No, it's the second part of part 2 and part 3.
Ah, I see. Okay. All right. Yeah, on computation group 3.
Yeah.
So, take it away.
Thank you very much.
I'm just going to run and check.
Yes, yeah. Good morning. Thank you very much for still coming despite yesterday's talk. What Josh said, we will split into groups and subgroups. That's actually the perfect segue into my talk because we will split groups we will split them in the rather hard way, as we'll see in a moment. Well, let me briefly review where we were yesterday. We looked at the bottom layers of the CGT stack at basic functionality for computational group theory. We have the stabilizer chain data structure for permutation groups, and we have seen that works well but assumes that the size of the domain is much smaller than the order of the group. And that will imply that we have short orbits, that we get a stabilizer chain on multiple levels, and it really splits the group apart nicely. But if we have a matrix group or some other group of automorphisms of some structure, this is not guaranteed. And not only is not guaranteed that we can't prove it, but you can easily construct examples where it will fail horribly. And it will fail horribly because there is no subgroup of small index, so there cannot be any action with a short orbit. And if the orbits are long, the stabilizer chain degenerates to a single layer or just 2 layers or so, and we don't really have a divide and conquer algorithm. So let's go back and look at a different approach which uses a little bit more of algebra. And one of the basic ideas in algebra is to look at, well, structure preserving maps, homomorphisms. We can look at homomorphic images as approximation of a structure. And the nice thing in algebra is that approximation is a homomorphism. So all the trouble other approximation ideas like numerical analysis have with error propagation, we don't need to worry about. Homomorphism says errors stay fixed. They don't accumulate. So we want to, and in such a case, we would like to reduce a calculation in a group to a calculation in the image of the homomorphism and the kernel of the homomorphism. Well, slight caveat, there is some extra work. It's not in a group, it's not just image and kernel. There is the question how image and kernel are put together. There is some extra glue which goes under the name of cohomology, which connects image and kernel. The easiest way to think about it is probably if you look at matrices, a block upper triangular matrix is not guaranteed to be convertible to a block diagonal matrix. You might have an off-diagonal block which has something in there, and basically that thing, if you can't put that away, if you can't change this to 0, that's what cohomology describes. But what one can still do is you can calculate in the image, we do something in the image which gives us an element which has a trivial image, and that we put into, that will lie in the kernel, and then we do a calculation in the kernel. Yeah, in these cases, for example, the order of the group is order of the image times order of the kernel. We will need generators for the kernel, and we'll get to that in a little moment in a topic called presentations. Constructive membership in the group would be constructive membership in the image, express the image of the element in images of the generators, divide that off, that gives us an element which is trivial in the image, and then do membership in the kernel. So that's the idea I want to use. Before going there, I very briefly want to talk about random elements, because a lot of the methods which we are going to use involve random elements. Well, if we have a group given by generators and we want a random element of the group, well, we need to form a product of the generators, a random product, there are a couple of questions which come up. We want the random elements with good quality as equally distributed over the group as one can hope for, and so questions come up, how long words would one need to form, what's the quality of elements then, and the method which is used, which gets a little bit around this long word question, is what goes under the name of product replacement. It basically is a random walk on generating k-tuples of a group. Why a random walk? Because there is a lot of theory in statistics which deals with random walks, and so there has been a lot of work done before which could be used. Basically what we do is we initialize a k-tuple by taking the generators and pad with some identity elements or other, or just duplicate generators. And then the step in this algorithm is we take one element in the tuple, we replace it by the product of this with some other element, or by the quotient of this with some other element, and we return that entry. Clearly, this will transform a k-tuple to another k-tuple, and there is an initial mixing stage to get typically around 100 times or so to get some random distribution. The nice thing about it is it's a relatively cheap operation. It's just a single multiplication for each random step. Because it's based on random walk theory, one can actually make statements about the quality in theory. In practice, the random elements one gets this way are pretty good. Of course, there are still a lot of open questions. Generically, what can one prove about the quality of random selection? And there is a lot of potential work possible about what it really means, and how would one say, what would be good methods for selecting random elements in groups. Okay. But I assume I have this, so with a group given by generators, that I can pick reasonably approximated random, equally distributed random elements. Okay, so the next topic I need is what is called a presentation. And I'm not sure whether you've all seen this. So the idea is that we can write every finitely generated group as a quotient of a finitely generated free group. And since it's a quotient, there is a kernel. Generators for the kernel as a normal subgroup are called relators. And what we get is something which you've probably seen for describing groups. We give certain generators and we give certain identities which have to hold among the generators. And these identities we call relations or relators. And then one can show, that's not very hard, it's just tedious to do, that this always will describe a group. The difficulty is, if I write something like this randomly, it could be that the group is smaller than I hope. So this tells me I can write a square is 1, but this does not guarantee that a is an element of order 2. That just guarantees that a is an element of order dividing 2. So if you write down some random relations, your group, there will always be a group that will always define a group, but the group might be smaller than you expect. It might be trivial, because they're always just saying that certain things are equal or certain things are the identity. Yeah, in this case it works. This would be a description of the alternating group on 5 letters. In general, working with presentations, if someone just writes down a presentation randomly, this is a very hard question. Very hard in the sense of that it has been proven it's impossible in a Turing machine model to actually do it with an algorithm. To determine what the group is, how large is it, or even just to determine is the group trivial or not. But in many cases there are plausible methods for finding out information. I won't talk in these lectures about these methods, but if you're interested, I'm happy to talk to you in private. what they are doing. But if we have some kind of normal form, that these representations actually work reasonably well. And we will be using such presentations for describing a group which we know, or where we assume we know it already. So
what exactly do you mean when you say a presentation is written at random? Is that a distribution you're drawing from?
No, that's just, so question is, what do I mean by presentation at random? That's just a colloquial random. If you go out and you ask someone, write down a presentation, and then you give me this and you ask, what group is it? That is a very hard problem if you don't know nothing where it comes from. If they are just some strings, that is a very hard problem to say what is the group. But if the presentation satisfies certain conditions, if it comes in a nice way, often you can say far more about the group. Yeah.
There are models of random presentations. They don't get interesting.
Yeah. Thank you. So what can we do with the presentation, or what are some aspects of presentation which I want to use here? The first one is we can use presentations to describe extensions. In group theory, an extension is to describe a group as being put together from a normal subgroup and a factor group. And this business, which I said, that's cohomology, actually one can describe nicely using a presentation. So if we have a presentation for a normal subgroup and a presentation for the factor group, we can put them together with some extra information and build a presentation for the whole group. So if we want a presentation for a group, we can build that presentation from its simple composition factors. And for simple groups, there are certain presentations known. For example, for groups of Lie type, the Steinberg presentations. Well, there is a slight difficulty here. If we want good algorithms and we are working with the presentations, we need that the presentations are not too long. Because if the presentation is longer than our input size, or is even not polynomial in the input size, we can't even touch every relator in the presentation. And so the Steinberg presentations alone are not good enough for algorithms because they are too long. So one needs some further work to make the presentations short. And alas, there is one class of simple groups, the regroups, for which still no short presentation, short in a certain technical sense, is known. Or I should say, I'm pretty sure I know the short presentation, I just can't prove that it always works. And that is a rather hard problem, and a lot of interesting results about being able to do certain things in polynomial time for groups actually just hang on this one case. So the existing state would say, as long as this kind of group does not occur.
When you say that you know the presentation, but you haven't, I mean, has it been proved, for small examples?
Yes, yeah,
What
yes.
size, I mean, what?
Size is, so these groups occur, so the question is, what do I mean by I know the presentation? So these groups exist over fields in characteristic 3. Exist over fields mean they have a natural way to write them as matrix groups, and actually from the way how they are constructed they have in relation to these fields, to fields in characteristic 3 where the exponent is odd. And so I can show it for about 3 to the 7, 3 cubed, 3 to the 5, 3 to the 7. I've shown that it works. I think I could show it for 3 to the 9. The small regroups, yeah. But beyond that, because the groups are not order of the field, the groups are a polynomial in the field order, roughly, yeah. And then it gets too large and I can't do it.
But there's a conjecture.
There is a conjecture, though that conjecture is not really spelled out in a paper. Yeah. And I can tell you more than you want about this. I have some really scary slides about that. Okay. But if we have a group, we can build a presentation, at least in principle, we can build a presentation from presentations for simple groups. Second remark, if we have a presentation for a factor group, and we evaluate the relators for the presentation in the corresponding generators of the factor group, well, they will give us always the identity in the factor group because they are identities which hold in the factor group. And in fact, they give us normal subgroup generators for the normal subgroup. So, if we have a homomorphism, we can describe the image sufficiently that we can write down a presentation for that image. This presentation will give us generators for the kernel. And we are going to use that to get the kernel. So with presentations, we can again solve the problem of how do we get from generators to generators. Generators of a homomorphic image are trivial. They're just images of the generator. Generators for the kernel come from a presentation. And the third important use is, I talked last time about that we have problems with, say, a lot of Schreier generators arising in stabilizer calculations. We also might have here certain algorithms where we make random selections and things could go wrong. And when things go wrong, the situation will always be one-sided wrong. It will be wrong in the sense of that the algorithm will think the group is smaller than it actually is. Say because we're missing some generators or we have thrown away some generators we better shouldn't have thrown away. And what verification does is, and I'm not going to show you the details how it does, but the idea of verification is, we say, let's assume everything went fine. There might be situations in between where something is dodgy and we've already found out that actually something went wrong. But let's assume everything went fine and we get a data structure at the end of the algorithm. From that data structure, we build a presentation. And the presentation is like a suit for the group. And but it's built based on the description the algorithm found. If the algorithm thinks the group is too small, it builds a suit which is too small and the group will not fit it. So, by building a presentation and evaluating relators for that presentation, then in the original group we can see whether something went wrong because some relators will then evaluate not to the identity. And that's the verification which we can use to make the Monte Carlo algorithms, Las Vegas algorithms. Okay, so that's what we use presentations for. I mentioned already, so if we split things apart, we have normal subgroups and factor groups. What are the atoms when splitting things apart? And this is something where group theory actually has a lot of theory available which really describes these atoms. And that's something which it really is crucial to this kind of approach. So, the atoms are groups which we cannot cut smaller where there is no non-trivial normal subgroup. And such groups are called simple. Well, the first important theorem there, and that's something you've typically seen in a first graduate abstract algebra class, there is the Jordan-Hölder theorem, which says that these atoms, they're really, in some way, they have the properties we would hope for atoms if we look at the composition, simple composition factors of a group. they are unique, including multiplicities. So there isn't, this is like unique factorization of integers. It's not that we can chop it in different ways and get different results, but they really belong to the group. And that's a result which is over 100 years old. The other result, which is, depending on how you count, 40 years or 20 years or minus n years old, is the classification of finite simple groups. So, there is a huge result, which is 115,000 at least journal pages. It's a result which was announced in 1982, but some last bits really were just published in 2004, and you can argue what is the chance that there are mistakes. So there is an ongoing revision, and this classification describes, is basically giving a list. It says, and I'll show you the list in a moment, if you have a finite simple group, it must be one of the following. And while you can argue about what is the chance of an error there, the general assumption in group theory seems to be that we might doubt the proof, but we believe the result. This is a bit like number theorists assuming the extended Riemann hypothesis or so. So for these algorithms, we assume this classification is true, and indeed, these are all the possible simple groups. Well, they could be cyclic of prime order. These groups, they don't even have any proper subgroups. That is very easy, or if you want, it's very hard because it's a discrete logarithm problem if the prime gets larger. Alternating groups, they are simple if the degree is at least 5, sorry, bigger than 4. And they're often, it has to do with some combinatorics to describe these groups. Then there are groups which are called groups of Lie type. What you should imagine, the prototypical example is the projective special linear group. So you take all matrices over a finite field. Well, and now there are some normal subgroups. First, you don't take all, but you take only those with determinant 1, because that gives you a normal subgroup. And you factor out the center. These are diagonal matrices with determinant 1. So this factor, that's called the projective special linear group. That is the prototype of such groups, and there is a huge amount of literature about these groups. So a lot of work has been done by mathematicians which describes the theory of these groups, which describes properties of these groups. And finally, as in a lot of classifications, these are all infinite series. Well, and then there are 26, one for each letter in the alphabet, 26 sporadic. Sporadic means they don't fit into anything else. Sporadic examples, they are ad hoc, but they are overall, because it's finitely many, bounded in order. So if we care about complexity, we don't really need to worry about them, but one can deal with them ad hoc. And the idea now is to say, can we use the fact that there is a lot of theory, a lot of knowledge about these groups, to basically move that any problems in calculation away. So the idea, if we look at what kinds of algorithms do actually exist, and then we look at the question, how does this work for groups? There are basically just 3 classes of algorithms which exist, if you look at them very broadly. There is linear algebra, or if you want to be fancy, you call it pair completion. These typically gives us good algorithms which are polynomial time, which work well, have nice theory, work well in practice. If you have a problem rephrased in linear algebra, you can hope to solve it. Okay, that's good. Well, then there are some algorithms which are really, where you might even say, is this worth calling an algorithm? This is just having the computer explicitly construct something by just writing down the result. Right? If you write a routine for identity matrix, that's not a very exciting algorithm. It writes down the identity matrix by putting zeros in and then putting ones along the diagonal. So they are algorithms. They are obviously very efficient, but they are, and then there is a huge class of algorithms which in some ways search, which construct possibilities, which try out things, and they run into a risk that they might be exponential time because we are trying out all possibilities. So that's what is difficult. And the goal is basically to say, can we move that class away? Can we use the fact that for simple groups we have a lot of theoretical information. Can we use that information to say, well, they're the problem, we just can assume it has been solved already and we can look it up and just write down the result instead of doing hard work. And the other case, the other composition factors are cyclic of prime order. They are so they have some relation to finite fields, therefore to vector spaces. Can we hope to use linear algebra there? And we will see later. I will try to give you a bit an idea how we are trying to do this. I'm not saying we have achieved this, but that's the goal. That's conceptually the reason for separating these simple groups or looking so specifically at the simple groups. But let's go back to the question of splitting the group apart. So, we want a homomorphism, we want an image, it has an image, we want a kernel. So then we can iterate. We go to the image, that's again a group, we go to the kernel, that's again a group, and we can try to find homomorphisms. So what we just need is basically some mechanism which for a given group either gives us a homomorphism where the image is smaller, and we might be happy even if it's not smaller in group size, but if it's smaller in the way how it is represented. And then we go to the image, get a presentation, get generators for the kernel, and we recurse in both cases, or that structure would prove that the group is simple. And in this case, we get a composition series. We actually get it in the form of something which is called the composition tree. So on the top, we have the group we start with. We have found some homomorphism phi. We go to the image of the homomorphism. That's another group. We work again in that group. From that, we get in the end a presentation. We go to the kernel. And at the end, we get, in this tree, we get leaves. And the leaves are the simple groups. And the simple groups exactly correspond to a composition series of the group. That's the basic data structure which is constructed by something which is called matrix group recognition. That's the modern approach for working with matrix groups. Of course, I said we take a homomorphism. Where do we find these homomorphisms? They don't come naturally. Well, in the world, if our group is a matrix group, presumably they will come somewhere from matrices. And therefore, what I want to do next is to look at matrices and at ways how matrices can give us homomorphisms, for example, to a smaller matrix group. And a basic case is if we have a matrix. So, let's say we have a matrix group, it acts naturally on a vector space, vectors over the same field in the same dimension. And this vector space, the posh name for this vector space is it's a module. Well, if there is a subspace which is still invariant under the group, then it's called a submodule, then we can We could look at the action on the factor module or the action on the submodule, and these will be matrix representations in smaller dimension, so they would give us homomorphisms to something smaller. So, how can we find submodules? And going back to my second slide, this process of finding submodules typically goes under the name of meataxe. And that's what I now want to describe. How do we find such submodules? So, we have, well, in abstract language, a module for an algebra over a field, finite dimensional algebra. We want to find a proper submodule or prove that that module is irreducible. If you don't like the abstract language, you can just think about it in matrix world. What I'm asking, if I have a bunch of square matrices, can I find a base change which will bring all these matrices into block triagonal form? I don't require block diagonal, I can't necessarily hope for that, well, I can't even guarantee that this is, but I would like to find, can I bring them into block triagonal form, which means I would find a subspace which is left invariant by all of these matrices. Left invariant in the sense of every vector in this subspace is mapped into that subspace. Yeah, is that idea clear? Okay, excellent. So, the first observation is a variant of the orbit algorithm which goes under the name of spinning algorithm. And what this algorithm does is it takes a bunch of vectors, here I call them V, and it gives me a basis, let's assume they're linear independent because that we can deal easily with, and it gives me a basis for the submodule spanned by these vectors. How do we do this? Well, the submodule will contain, if it contains a vector, it will contain all images of the vector, because otherwise it's not a submodule. And it will contain all linear combinations, because otherwise it isn't even a subspace. So, what we do is we start an orbit algorithm, and we start with the vectors for a basis spanned by the vectors we have here. In the orbit algorithm we get images, but now we don't add every image, new vector image to the stack, to the queue which we are processing, but we check before adding it to the queue, is it in the linear span of what we have so far? Because if it's in the linear span, we don't need it. So, take some vectors which are linear independent, which you put at the start in your queue, go through the queue, takes the next vector of the queue, calculate the image under every generator of the group, check does this image lie in the linear span of the queue so far. If yes, fine, so far everything okay. If not, you add it to the queue and you go through. Well, if this is a finite dimensional vector space, you can only finitely many add a vector because every time it increases the dimension, so this will have to stop at some time, and when it stops we have found a basis for the smallest submodule which contains the vectors we start with. So, for finding submodules, therefore, it is sufficient, we don't need to find the whole submodule, it's sufficient to find a single vector which lies in a proper submodule. Right? Because the spinning algorithm then will give us a submodule. So, how do we find such a single vector respectively? Even more interesting, how would we show that no such vector can exist? And this is a very clever criterion which goes under the name of Norton's irreducibility criterion, named after Simon Norton, who invented this. Simon, unfortunately, earlier this year died. Yeah, so what this is basically, this is an irreducibility test for a module, and it comes with a one-sided witness. If it tells us the module is reducible, it actually gives us a vector which lies in a proper submodule. And it's a test which works very efficiently, and gives us, either proves the module is irreducible or it will give us a concrete way how to find a submodule. Namely, the criterion is the following theorem. Let's take, so we have an algebra of matrices acting on a vector space. I'm interested in the case of groups, but this is not really, we don't need groups here. This works for arbitrary matrix algebras. So it says, pick an element in your matrix algebra which has a non-trivial kernel. Such elements clearly exist. For example, the zero element. In practice, we will not want to use the zero element, but for the proof that's existence of such elements. So, such an element will be a linear combination of products of the generating matrices. Well, and now the theorem says there are one of the following things must hold. The module might be irreducible, or if it is reducible, there might be a vector in the kernel of this element, right? This is a matrix, such that the submodule spanned by that vector is a proper submodule, or there might be in a vector of the transpose of that matrix, which gives us a proper submodule. So, if you feel uncomfortable structurally, what does it mean to transpose? Basically, that's a statement about the dual module. And if you find that a vector spans, in the null space of the transpose, spans a proper submodule of the dual module, you take null space and transpose, and then you get generically a proper subspace here. So, this is really just dual module. So, why is this a useful criterion? Because it tells us we don't need to run through all vectors. Well, that certainly would work. If there is a proper submodule, there must be a vector in a proper submodule, so we could run through all vectors. But all of them are quite a lot. So, we will hope to find elements where the null space is quite small. And this is telling us you only need to run through a much smaller search space. Right. So is clear what this criterion says? And I will give you in each lecture, you should try at least to give one proof. I will give you a proof of this theorem. And the proof is actually the proof is on the level that you could do it in a first linear algebra class. Because you really don't need anything more than writing down matrices with respect to a basis. So, this theorem says one of the following holds. And what I will prove is I will assume one does not hold. So the module is reducible. And I just need to show that either this or that holds. Right? So let's assume the module is reducible. And then I can find a basis where I write the matrices. If I do a base change where all the matrices get such a block triagonal form with a zero block here. That's just saying there is a submodule, right? And I'm acting on the right, that's why my zero is here. If you like, I'm acting on row vectors by right multiplication. If you prefer acting on column vectors with left multiplication, your zero would be here, but then the same proof works. Just with transpose. So, we will have this form, and I've written the element B, which was this particular element in this basis. So, we get this element also in this block triagonal form with a block B1 here and a block B2 here. I said that element was supposed to have a non-trivial kernel, so the determinant of this matrix is 0. What is the determinant of this matrix? It's the determinant of this block times the determinant of this block. So this determinant is 0 or that determinant is 0. So let's first look at the case that the determinant of B1 is 0. Well, if the determinant of B1 is 0, I can find a vector which lies in the span of the first few basis vectors, right? Then B1, the matrix B1 has a non-trivial kernel. If I take a vector which lies in the null space of B1 and I pad that vector with zeros to make it to the right length, this new padded vector will lie in the null space of the matrix B. So I have found a vector which lies A in the null space of this matrix B, but this vector has a form that it's padded by zeros, that is just in the span of the first few basis vectors. And the span of the first few basis vectors, that is the submodule. That's how I've chose my basis, that the first few basis vectors are the submodule. So I have found a vector in a proper submodule and it lies in the null space of that matrix. Second case, what happens if the determinant of B2 is 0? Well, then I do the same with a transpose matrix, or the same in the dual module. And I get, by the same argument, a vector there. So, that's the criterion. How do we use it? We run through all vectors in the kernel up to scalar multiples. In particular nice if the kernel has dimension 1. The dimension of the kernel in this context is often called nullity, and in that case we just need to test one vector because clearly we need to run up through these vectors only up to scalar multiples. Right. One can't guarantee this all the time, but in many cases this works quite well. So how do we find such elements which have a kernel of small dimension? The first proposal, and that's actually where the idea of this approach, which goes under the name of meataxe, comes from, is in a paper by Richard Parker from 1982. What he says is just pick some random linear combinations of products in the generators. And actually his random is, he gives you a list of 10 words in the generators where he says, try these and in everything I've done, always one of them worked. And that is purely heuristic, that is, try this, it works, but there was basically no theoretical analysis, it just happened to work. Well, we can do better. We can actually try to be more clever, not just to pick a random element, but form some element in the algebra as a linear combination of generators, or even form some element in the group, look at its characteristic polynomial, factor it, and evaluate a factor of the characteristic polynomial in that matrix. If your characteristic polynomial has a linear factor, you get automatically from this an element which has a null space of dimension 1. A linear factor with a multiplicity 1. So one can do this by looking at the characteristic polynomial. That still doesn't give us a polynomial time algorithm. There is a subtlety, and that subtlety, the difficult case, is basically a case where you're missing roots of unity. So imagine, and it's in some way the most boring group, look at a cyclic group of order P. And you are over a field in a characteristic co-prime to P, so you do not have Pth roots of unity. Okay. And now you take, say, the regular representation of this cyclic group of prime order. Well, if you would go over an extension field, this representation can be diagonalized, right? It can be diagonalized to just have roots of unity on the diagonal, but you can't do this over the field where you are because you do not have these roots of unity there. But in such a case, you can show that basically just the zero matrix is the only element with non-trivial nullity. And that's slightly awkward because then one would need to run through the vector space. So there is extra work, and this has been proven by Gabor Ivanyos and Klaus Lux. They have, with some additions which I'm not going to talk about here, but basically there are results which now say yes, that actually this meataxe approach gives us a polynomial time algorithm, polynomial in the size of the input. So if you give me a set of matrices over a finite field, there is a polynomial time algorithm which either proves the natural module for these matrices is a simple module, or it gives me a proper submodule. Okay. And that's the basic version of the meataxe. But that's not all. There is something else what one can do with a meataxe. Namely, one can build further things from it. And I just want to give you a very vague idea of one of these cases, namely isomorphism of simple modules. In fact, what is typically meant when people talk about meataxe, they mean a package which has further higher level functionality. Namely, it starts with, we take a module, we look at it. If it's not simple, we look at submodules, factor modules, we recurse to these. In the end, we get simple composition factors for the modules and matrices for the actions on the simple composition factors. We test for isomorphisms between these simple modules, so we get the composition series up to isomorphism. And there is further functionality which finds all submodules of a module, basis for all submodules, or finds a decomposition as a direct sum of indecomposable submodules. And from this one can actually build module automorphism, group isomorphism of module, test isomorphism of arbitrary modules, not just of simple modules, but this is somewhat more involved. So here I just want to look at the question, how can we test isomorphism of two simple modules? If you have two simple modules, obviously matrices in the same dimension over the same field, how do we test whether they're isomorphic? So let me briefly show you this. So I have two matrices, two matrix actions, and now, I had hoped, actually, let me do this. I know this is not perfect for those on the video, but they can look at the slides separately. So I have some algebra A, and I have two different matrix representations. I have a representation phi and a representation psi of the same algebra. If the underlying modules are isomorphic, I now look at an element B, which I'm getting, right? That's what the meataxe did. It looked at an element B with non-trivial null space. If the modules are isomorphic, then the image of B under the one matrix representation must correspond under this isomorphism to the image of B under the other matrix representation. That's what isomorphism means. And that means the isomorphism also must map the nulls, or the corresponding matrix must map the null space of this matrix to the null space of this matrix. Let's for simplicity assume the null space just has dimension 1, otherwise one needs to try out some possibilities. Well, if the null space has dimension 1, that means a basis vector here under the isomorphism must be mapped or I can assume without loss of generality that a basis vector here is mapped to a basis vector here. Why to the basis vector? Because the rest is just scalar multiplication, and scalar multiplication always will be an endomorphism of a module. So I don't need to worry about scalar multiples. So the vector in the null space, a vector v here, is mapped to a vector w here. And now, if my module is simple, this vector v will span the whole module under action of the algebra, and that vector will span the whole module under the action of the algebra. So I now start calculating images, and I know, let's say I have an image under an element a phi here. That element, and let's assume this is linear, these two are linear independent, so this is a new element I can choose for a basis. Well, then this element must be mapped, if there is an isomorphism, to the image of this vector w under the action of the same element A, but under the other matrix representation. And so on. So, I take this single vector here, and I now run a simultaneous spinning algorithm. I run a spinning algorithm on this vector v, which will build me a basis of the whole module, because the module is simple. That's where I use the module is simple. I run the same spinning algorithm here. What will happen? It could happen that I get some inconsistency, that I get images here such that the corresponding, which are linear independent, such that the corresponding vectors here are not linear independent, or vice versa. If this happens, the modules cannot be isomorphic. But if that not happens, if I have linear, if I calculate a new image and I get linear independence here, if and only if linear independence is there, I have in the end built up a basis for the whole module, and I know the isomorphism must map these basis vectors to these basis vectors, and I have written down the isomorphism. So that's how I can test for isomorphism of modules. Yeah, and now let's going back. So that's what the meataxe does. It takes a module, it finds submodules. Actually, it will find composition factors of the module, include up to multiplicity. Right. So, what have we done? We came actually, the meataxe went a little bit as an excursion. We really started with the question, if we have a group of matrices acting naturally on a vector space, how can we find a non-trivial homomorphism? And I said, one way of finding such a homomorphism is we take, we find a submodule, and the homomorphism is the action on the submodule or the action on the vector module, whatever you prefer. And the meataxe gives us some way for finding such submodules. Of course, if the module is simple, such submodules don't necessarily have to exist. But there are other ways how one might be able to decompose the module. So, even if the module is irreducible, there might be some other structure how one can take that module apart. And you don't really need to understand all of these ways how it might be taken apart. If you think about it, just there are some other ways and other homomorphisms that's perfectly good enough for understanding the following slides. But let me just briefly mention some of these ideas. So, you might have a wreath product action. Your module might be writable as a vector space, as a direct sum of subspaces, where these subspaces are permuted amongst each other under the group. Right? That's, for example, if you have permutation matrices, your subspaces would be just the spaces spanned by the basis vectors. They are permuted amongst each other, but they're never mixed up otherwise. Then you get a Reith product substructure, subgroups of a Reith product. The module might be writable as a tensor product, or you might have analog to the Reith product structure here, a tensor Reith structure. The module might be actually writable over a smaller field and is just written over a field which is too large, and so forth. There are various ways how one can find such geometric decompositions. I should say that not all of these have really good algorithms. There are good algorithms for meataxe submodules. There are good algorithms for these Reith products. The tensor product cases don't yet have algorithms which in practice work well, but really don't have a good theoretical solution. But if we can hope that, but we have these different ways how a module, the natural module of a matrix group, will give us homomorphisms to smaller matrix groups. Okay, and now there is a theorem which is named after the person who wrote it up, Aschbacher's theorem, written and published in 1984. By the way, this is it's a great result, but it is a horrible paper. The paper is basically a brain dump. It has 9 sections. Sections 1 to 8 are, what do I know about this topic? I will write down some theorems. You have no idea why these particular theorems are written in that. Section 9 says, well, now I will combine some of the results which I've stated before and prove the theorem. Anyhow, so Aschbacher's theorem says, if you look at the natural module for a matrix group, so the vector space where this matrix group acts on, then either there is a geometric structure which is preserved, which I can use to build a homomorphism to some smaller group, and build the homomorphism in a sense that through base change or through something I really can build this homomorphism, or the group is almost simple. Almost simple means it's a subgroup of the automorphism group of a simple group. So if you do case distinctions, it's very easy to do a case distinction if you have a class of other, right? If you're cleaning up your office, at least for me, initially it goes very quickly, and then I find some things where I don't know where to put them. They are in the other category and I put them on the side. And the problem is that the other category tends to grow. But here, what this theorem says is, your other category is actually not that large. You know what comes in the other category, it's just almost simple groups. And with the consequence of the classification of the finite simple groups, there is something which goes under the name of Schreier's conjecture. Actually, from almost simple, we can easily get to a simple group by just picking some commutators. So what can we do at this point? We can build with this theorem, we have a matrix group, we can build homomorphisms to smaller images, and we can do this as long until the groups at the end are almost simple groups, and actually from this basically to cases where the groups are simple groups. So what is left is simple groups. How do we deal with these simple groups? And there we use something which is called constructive recognition. So these are the leaves of the composition tree. This meataxe and Friends algorithm builds this tree structure. The leaves are groups which we can't reduce any further, which are simple groups. What we now want to do is not just to say these are simple groups, but we want to say this leaf is this particular simple group, and we want to write it in a way how one would write down this simple group in a natural way. So if this simple group is the alternating group, isomorphic to the alternating group on 17 letters, we want to have an isomorphism which we can practically use, which we can go both ways, which allows us to write these elements instead as matrices, as permutations on 17 letters. If it's a PSL 519, we want to have a way how to write it as modulo the center as 5 by 5 matrices over the field with 19 elements. And we do this by basically finding elements from random search, suitable elements from which we can build the underlying combinatorial or geometric structure, where action on these elements corresponds to action, say, of the alternating group on points, and we therefore can write down if we have an element in this group we don't know, how we can write down the corresponding permutation. And then we use a presentation for the simple group to show that it really is the group we thought, that we get proper, that the map is indeed a homomorphism, and we hope for further calculations that we can use results from the literature about this simple group, which we can pull back to our group and thereby solve more involved problems. So, let me briefly just give you a glimpse how this constructive recognition works. I mean, I said very vaguely we want to build from elements this structure. So, the case I want to look at is the case of an alternating group, and actually there is a case distinction depending on the degree, depending how on congruences of the degree, and here I'll just look at the case that our degree would be congruent to -1 modulo 6. In this case, I'm looking by random search for an element in the group which is not trivial, such that the 3 times n minus 4th power is 1. And why do I care about this? In this case, with this congruence, this n minus 4 cycle is of a length coprime to 3. So if I have an element which has this form, this element must consist of a 3 cycle and an n minus 4 cycle. Or, well, it must have a power which has order 3, and it very likely has such a cycle. And from properties for these groups, such elements are found with a probability bounded from below. And I should mention that this approach, this is in a paper from 2003 by a couple of authors. So, we search for a random element such, and one theory shows there is a fair chance that we find such an element with this property, and quite likely this element will have this structure. So if I take the n minus 4th power, such an element then will be a 3 cycle. So then I have a single 3 cycle. Now if I conjugate a single 3 cycle with another element in the group, I get again a 3 cycle. And if I have 2 3 cycles, I can look at the order of their product, and that tells me whether the points which the 3 cycles are involved with, whether these points overlap, right? If you have 2 3 cycles and their product has order, and they don't share a point, their product has order 3. If you have 2 3 cycles and they share 1 point together, their order is 2, and if they share 2 points together, their order is 5. So I can test with this, whether conjugates of my 3 cycle are 3 cycles which don't overlap in points or say overlap in 1 point or in 2 points. And thereby I can choose certain conjugates which will correspond. Because I can label the points as I want, I can assume my first 3 cycle shall be the 3 cycle 1, 2, 3. Now I find from orders a conjugate which just overlaps in one number, and I can assume the new number that it would involve the numbers 2 and 3 again and have involve the new number 4, and so forth. So I can thereby build conjugates in my original group which correspond to standard nice generators of my of the alternating group AN. And how do I evaluate the isomorphism? How do I go from elements in my matrix group to these permutations? Well, if I want to know what, for an element X, what is the permutation image, conjugate, say the generator D1 by X, then I know that conjugate must involve the points 1 to the X, 2 to the X, 3 to the X. That's how conjugation of permutation works. And by looking at products of orders of products with these generators, I can find out exactly which numbers are involved, and from that basically build the permutation. So I can start with matrices, or I don't even need matrices, I just need that I can calculate bounded order elements. And thereby build an isomorphism, and an isomorphism which I really can evaluate from this group where I don't know much about, just the isomorphism type, to say in this case an alternating group given by nice permutations, and that's how I can pull over the theoretical information. Okay. So, in the last 20 minutes or so, let me go to the third talk. Yeah?
I know some of this extends, but how much of this extends to, say, arbitrary, finite dimensional associative algebras?
So the question is, how does this extend to associative algebras? The idea of splitting certainly works, and you can use the meataxe or fringe from the meataxe to try to find certain ways how you can decompose it. What I don't know is whether you have anything like Aschbacher's theorem, which says you basically need a characterization. What are the things which you can't cut, where none of your reductions will work? Or in some way you need to find sufficiently many reductions that your other category consists of objects for which you have a theoretical description. And that's why Aschbacher's theorem comes from 1984. That is not a random year. That is just after the classification of the finite simple groups was announced. Because at that point you can say, yes, it makes sense to reduce to a case where the other class is the simple groups, because I now have a description of the other class. Before that, there is no reason you could have proven, there is nothing in the proof of Aschbacher's theorem which really requires all the mathematics up to 1983 or so. Probably if you would have shown that proof to Burnside or Schur or so, they would have said, yeah, okay, I know, yes, or Weil, I think Hermann Weil easily could have proven Aschbacher's theorem. It's just, he didn't care about it. It wouldn't have been an interesting theorem for him, because the other case where it reduces to was something which was completely out of reach. The important thing is the classification tells us you have a hope of describing the rest, the things which hang in your filter, which don't go through smoothly. And that I don't know what is with algebra. So if you have anything like that for algebras, you could use it. Otherwise, you will get stuck at the point where you say, none of my reduction works. What can I do with it? It's a nasty guy, yes. You need to know you need to have a list what your nasty guys are. And for group theory, the amazing thing is that you have this, after all, relatively short list of cases which are simple, which happen to be the cases where no further reduction works. Okay? So, this is now 5,000 feet down. We are on ground level, at least here. I want to give you also, given where we are with time, an idea how further algorithms build on this. This is really just aiming to give an idea, and some of the things might go relatively quickly. So, the first step is, and say we want to calculate maximal subgroups or all subgroups or conjugacy class representatives of a group. How do we do this? Well, what we can do is, if we have a composition tree, we can act on the simple composition factors. And that's a little bit subtle how to write down this action, but basically what one can do from the composition tree, build a homomorphism where composition factors get permuted and probably some automorphism action on each composition factor. So we get a homomorphism into a wreath product of the automorphism group of this simple group with a symmetric group. What does wreath product mean? Wreath product simply says you have a group, you have multiple copies of this group, and now you allow yourself to permute these copies amongst each other. So it's a very regular structure, and one can build this homomorphism, and then one can show that the kernel of this homomorphism is the largest solvable normal subgroup of the group, which is called the solvable radical. So, the structure of the group de facto looks like the following. We have on the bottom this radical, this largest solvable normal subgroup. And what does solvable, what was the definition of solvable? Solvable, the definition is every composition factor is cyclic of prime order, or if you look at a chief series at subgroups which are normal in the whole group, you always have vector spaces. This group is composed from vector spaces. And that's the bit where I said here we hope to use linear algebra or linear algebra-like tools. Well, some problems still are hard for such groups. We learned yesterday that isomorphism of P groups is in some way the hardest case of isomorphism. But for this we hope to use techniques which build on linear algebra. For the factor now has a particular structure, namely we have simple groups of one type here. These simple groups are permuted amongst each other and possibly automorphisms on each factor. Well, and we might have different types of simple groups. But here we have a combinatorial structure where a very large part of this structure is just these simple groups, where I hope that there is enough theory that I can look up results about these. And the hope for this is to build algorithms which do one thing in the factor which uses very much the simple group structure and refer to theory as much as possible, and then do something here which involves linear algebra to extend the result. yeah, let me skip this. This is how to, a piece polycyclic generating set is like a composition of bases for these multiple vector spaces. And you get algorithms which fit under in a scheme which is called solvable radical or trivial fitting method, which says, on the one hand, first calculate the problem, solve the problem you want to solve in the factor modulo the radical. And that factor, it's a, yeah, this has a very particular structure. There is so much just this big direct product of simple groups. Reduce it to these cases. This is a group which can be represented by permutations in relatively small degree, and then lift the result iteratively over elementary abelian normal subgroups one by one, always adding a vector space below. Right, do I want to do that? Maybe again for time reason, let me skip this. So there is one version, or let me just very briefly talk. So one can, for example, do an orbit, a better version of the orbit algorithm. What do I mean by better version of the orbit algorithm? In the basic orbit algorithm, you calculate image of every point under every generator. Well, if you have a normal subgroup, the orbits of the normal subgroup form what is called blocks. They stay together. An orbit of a normal subgroup must be mapped to another orbit of a normal subgroup. So, in the orbit algorithm, when you get a new point, you take a point, you calculate an image. If the image is new, the whole block, the whole orbit under the normal subgroup must be new. And you get a new element. So not only do you have fewer images to calculate, you can also do something analogous with Schreier generators, and you get far fewer Schreier generators. Basically, every time you have a normal subgroup and then a factor, you calculate first the stabilizer in the normal subgroup, you calculate a stabilizer of the orbit, a stabilizer of the block, and then one just needs to do some modification of generators to get the stabilizer here. And that severely reduces the number of Schreier generators. In the best case, you actually just get 1 or 2 generators for each composition factor in the stabilizer as new generators. And with this, we get a whole battery of algorithms which originally have been, this paradigm has been used originally for permutation groups, but now with a composition tree we can use that same paradigm for groups for matrix groups, and we can calculate conjugacy classes of elements, of subgroups, whole subgroups, therefore pseudo subgroups, element centralizers, subgroup normalizers, maximal subgroups. The surprising thing is that in this context, actually, maximal subgroups is a comparatively cheap operation. It's much cheaper to get just the maximal ones than to get all subgroups. We can there are algorithms for automorphism group, for isomorphism test. These algorithms, well, the idea of using the solvable radical goes back to a paper of Babay and Beals from the late 90s. Then there is a whole series of papers by Cannon, Holt and others, and some papers by me with co-authors which describe some of these algorithms. I also would like to point out one paper by Jean Lux and Takumi Miyazaki, where they actually do a theoretical analysis of the normalizer question, and they get, which in some way is using the same idea, and they get a very interesting result. Because they get a polynomial. These algorithms here are mainly practically consideration. They do not do any kind of complexity analysis. But they have a very interesting result. Namely, they can give a polynomial time algorithm as long as the non-solvable composition factors of the group are somehow bounded. If we say they are, the non-solvable case is at worst this, then you get a polynomial time algorithm. And a hope could be to have in general to extend this kind of result to some of these other calculations and to end up with algorithms which are polynomial time subject to how bad are the non-solvable composition factors. And yes, in some way their calculations might be larger, or you might have to say, yes, you hope this exists in theory. Okay. Yeah, given the time, I think this is a decent point to stop. Thank you very much. Yeah.
Questions? How much of, I mean, I know certainly a lot of this is actually implemented and available. Is it all, or are there things you've told us about which are yet to actually appear again?
So, it is implemented, it is not all implemented in every system. So, Magma has the full composition tree in a very effective version. If very effective means the authors feel, of the code feel this is something which is production code which can go out in the world and do great things with. GEP has currently so far a far more restricted version where more work has been done, has to be done, and that a lot of that work is implementation work, where theoretical descriptions of the algorithms exist, but they have not been implemented. As far as this goes, again, Magma might have a little bit more. These algorithms exist in the case of GEP, which I know better. They all exist for permutation groups. If you come with a matrix groups, you need to know what information to tell GEP to actually go through a composition tree. It will not do this by default. So you need to know the secret handshake to tell it how to go through a composition tree and use this. And the existing algorithms for conjugacy classes of elements, centralizer, normalizer, maximal subgroups, they already work. The ones for conjugacy classes of subgroups and automorphism group or isomorphism test, they should work in principle, but what do I mean by in principle? There are some subroutines, and it's basically questions like how to represent isomorphisms, which is not properly implemented, and therefore they don't yet work in these cases. So they would fall back to a permutation group case. Yeah, but that's the current implementation status. And obviously, if you're interested in more details or how to use it or so, I'm very happy to show you.